Good evening. It is with great pleasure that I introduce Chris Quigg this evening. Chris holds the title of Distinguished Scientist Emeritus at Fermilab National Laboratory, where he spent most of his illustrious career. He graduated under the supervision of J.D. Jackson. And I think that a lot of you know him because he was the author of an electrodynamics book where a lot of us have actually studied on. After his graduation at Berkeley, he embarked in a journey to shape the landscape of theoretical physics. His honors include the Sakurai Prize from the American Physical Society and the Alexander von Humboldt Prize from Germany. Chris has left an indelible mark on the field. His contribution spans many areas of theoretical particle physics, from his seminal work on electroweak symmetry breaking, pivotal to establish the theoretical bound on the mass of the Higgs boson, to his work on heavy quarks, quarkonia, ultra-high energy neutrino interactions. Chris' works knows no bounds. His ability to bridge the gap between theory and experimentalist set him apart from many of his colleagues. Chris is an engaging speaker, a consummate educator, and communicator. His book, Gauge Theory of the Strong, Weak, and Electromagnetic Interaction, is an outstanding resource to advanced graduate students, offering insight to intricacies of particle physics. Chris is now entering the realm of popular science. Along with Bob Cahn, Chris spanned Grace in All Simplicity, a captivating exploration of the journey to uncover the Higgs boson and unravel the mystery of the Standard Model. The book has garnered widespread acclaim, with critics praising its ability to make the complex accessible and the profound engaging. In extending our warmest welcome to Chris, we honor his remarkable achievements and his unwavering commitments to sharing the beauty and wonder of physics with the world. We welcome you.
Thank you. Well, that's too much to contemplate. So please come in. Thank you for coming tonight. It's a pleasure to be in Oxford once again and to have this opportunity to talk about our book, Grace in All Simplicity, which is here. This is a book which is about particle physics. So it deals with the ideas of particle physics. Importantly, it deals with the people of particle physics. And in a sense, it's a love letter from me and my co-author to the people who make our theories and our experiments happen, which includes not only PhD physicists and hardworking graduate students, but also the people who devise the tools and methods that we use in both theory and experiment. It's a book that's written with no equations, not even as wallpaper, no drawings, no graphs, no photographs. So we endeavored to explain everything we wanted to explain in words that would be intelligible to people with whom we would look forward to having a conversation. Another abbreviation for the audience of our book is people who enjoy long-form nonfiction, willing to make an investment of time in reading about things. And we take our audience very seriously. So there are certain demands made on the audience, but they're not in the nature of pre-existing knowledge or even pre-existing interest. So one of the things that strikes us, Bob and I are both voracious readers, although in slightly different domains. He loves Jane Austen. I think I read Pride and Prejudice only. and so our tastes are a little different, but both widespread. One of the things that has impressed us about the great essayists of our time, the people who write about all sorts of things, is that they are like people who are good at conversation. So we know from everyday life, and this is true, I'm sure, of all of you, you may start a conversation with a friend or an acquaintance or a stranger that's about a topic that's on your mind at the time that may not have occurred to the other person. And in a successful conversation, this will go back and forth. You'll elicit some responses from the other person. And the best people, the best writers of essays, are able to engage our interest in a topic that we had no idea we cared about before and make us care about it. So in our dreams, we would like to accomplish that in grace and all simplicity. There's an echo, but maybe not. So that is the plan of the book. As I say, it's about particle physics, and it will reveal all of the important ideas of particle physics. Unlike my textbook on gauge theories, after you read this, you will not be prepared to derive all the equations and to solve them for yourself. But you will, I think, have an understanding of the logic and structure of what we do and of the things that we don't know how to do yet. So let me say a few words about the organization of it. One of the things that's quite striking about our field today, and allied fields, which more and more have to do with the sciences of astronomy, cosmology, and so on, is that you and I live on the human scale. You know, an interval of a second or an hour, maybe even a year, the size of, well, a centimeter or a meter, a few meters our size, and so on. But we scientists have learned since the 1920s that in order to understand the world, we have to go away from the human scale. So I think the first example that we learn about in physics is the atomic physicists of the 1920s who understood that to comprehend why the floor is solid or why the metal gleams, we have to transport ourselves to a scale, to a size, 1 billion times smaller than the human scale, the nanoscale, now important for technology. And then when we go there, we have to learn the rules that prevail there and not expect that what we've learned in our everyday experience governs that world. And the great miracle, I don't know if it's a miracle, but it's a wonderful property of nature, is that what happens on that much smaller scale governs what happens on our scale and tells us how things work. So in the same way that we look at different distance scales, now in the study of cosmology back to the beginning of time, whatever that means, we're looking at distances as large as the entire universe and as small as we can make them. As small as we can make them is now much smaller than the atomic scale. So we are studying in our experiments at the Large Hadron Collider at CERN and elsewhere scales that are 1 billion times smaller than the human scale, and we have aspirations to go still further. And for times, we are studying phenomena that occur on the scale of a trillionth of a second, so really, really short times, out to much longer than the age of the universe. We in physics have developed mathematical tools that allow us to glide smoothly back and forth among these scales, and they're among the most powerful general tools that we have. So I mentioned the examples from atomic and particle physics, but this realization that we can't stick with the human scale actually pervades all of science in the 20th century and beyond. So if you think of some weird animal, I don't know, an anteater or a giraffe, something of your choice, well, you can go to a zoo and you see one of them and you say, well, that doesn't look like me, it's a very different character. But you won't know what that animal is unless you study its DNA, and in that way can make progress in discerning the relationship of that animal to other animals, to plants, and so on. So that need, again, to go down to a much finer scale than the human scale. And then if we're talking about animal behavior, unless you've seen the animals in a family or a herd, you won't really understand what they are. So it's one thing to see a giraffe in a zoo, a whole herd of giraffes in the veldt in South Africa and the other countries of the South. So this idea that you have to back off and zoom in order to understand what's going on is, I think, pervasive in physics. We all know the impact, well, some of us who were alive at the time and saw the first picture of Earth taken from the moon by a human being. Somehow it mattered that it was a human being. And to see us little, the famous pale blue dot, the little blue dot, we'll see that our perspective changed in the course of doing that. So let me tell you a little bit about the book itself. I'd like to read a few passages. We try to, it's not a textbook, so you don't have to master material going from one chapter to the next. We try to introduce ideas and episodes by making contact with things that you and I know as ordinary, not that you're ordinary people, and to make connections with that. And the first chapter, the beginning of the book, has to do with evoking the great passion that scientists and particle physicists in particular feel and act on in order to get to the root of what nature is about. So I'll read a little from that. Thunderstorms visit most of Europe only 11 days a year, but during the summer season on Monte Generoso in the Italian Swiss Alps, they give a breathtaking performance every other day. Afternoon clouds sweep in, welling up deep and rich as bruises, purpling the waters of Lake Lugano, nearly 5,000 feet below. Lightning slips down the throat of the sky like a shot of grappa. Thunder echoes majestically through mountain corridors. The next morning, the newly washed air reveals the great canine of the Matterhorn 60 miles away. Now and then, Monteviso appears, a faint obelisk of snow more than 100 miles to the southwest. Visitors to Monte Generoso in the summer of 1927 found new reason to be conscious of the might of thunderstorms. A net woven of iron cable, nearly half a mile long, stretched between the summit and the edge of a ridge 500 feet below. At night, a corona of bluish-green light, sometimes many yards across, shimmered across the net, as mesmerizing as the aurora borealis. On several occasions during storms, loud reports sounded once a second from the vicinity of the net. According to a dispatch published in the far-off New York Times, the hills rang as if a giant machine gun were laying a barrage on the enveloping clouds. That was science writing in those days. One can picture summer residents exchanging reports and speculations over aperitivi about the construction on the ridge and the three young men from Berlin who were leading the work. Did the displaced northern lights and the rapid-fire thunder mean that scientists were able to control the weather? Or had engineers devised a means to collect energy from thunderstorms? A persistent theory, endlessly embroidered, was that the young Germans were trying to harness the power of the atom so that the world could dispense with oil and coal. Liberating atomic energy was not the immediate goal that drew scientists to Monte Generoso, but the tales invented to account for the strange goings-on nevertheless contain more than a grain of truth. By recreating Benjamin Franklin's mythic kite experiment on an epic scale, the three young physicists hoped to summon from nature enough energy to dismantle the atomic nucleus. So this is lunacy to try to do this, but there was an important problem to find out after the discovery, the invention of the atomic nucleus, to see not only could you tear atoms apart, that was easy, but could you tear the nucleus apart and learn what it was made of? And these guys had a way of doing it. They hoped that would lead to success. Sadly, the next summer, they returned, having in the first summer accumulated voltages of about 18 million volts, especially during thunderstorms. They came back the next year determined to do experiments and try actually to knock apart nuclei. Sadly, during that summer, one of the three, a man named Kurt Urban, who had been publicized world over because he was they had a what physicists, experimenters would call a counting house. It was a metal hut in which he could control a wire that would reach up and down and span the gap that would be jumped by a lightning strike, an electric current. So he was publicized as the most struck man in the world, even though he was inside this metal hut and probably was never actually struck by lightning, but his ears were ringing, I guess, from being in there. So sadly, he fell from the apparatus to his death, and they abandoned this technique. Others with more modest aspirations in the laboratory, and not out in the mountains, did succeed in splitting the nucleus and gave us nuclear physics as it was known in the 1930s and then onward. I've been to Monte Generoso. It's a wonderful place. And I was treated by having a thunderstorm at night, so I got to experience all the things that we've written about there. Okay, so that's the introduction, which is intended to show that we physicists and other scientists are really committed to learning the truth from nature, and we'll do extravagant, sometimes slightly foolhardy things in the service of it. We, of course, today are much more careful in everything we do, but the passion remains there. So a second theme that we wanted to convey is the importance of tools, not just bright ideas, but tools for doing science. This happens obviously in the case of building grand accelerators, building experimental apparatus, but it also happens for theorists like me. We strive to develop methods, so theoretical tools that others can use, and we revere the people who have made particularly powerful tools that enable all of the rest of us to interrogate nature in different ways. So one of our chapters is about these people and our affection for them, our respect for them. And we begin again by an example that's not one that's in the laboratory today, but in more or less normal life. Some years ago, we visited a harpsichord maker in his New Mexico atelier. The artisan, a retired Caltech physicist named Bob Walker, showed us his materials, explained the various stages in the construction of a harpsichord, then treated us to a recording of Igor Kipnis playing Antonio Soler's Fandango on one of his instruments. But the object he took the greatest pleasure in showing was not a finished harpsichord. It was a block plane, clean, precise, and utterly apt, that he had built in order to sculpt soundboards of surpassing beauty and eloquence. This maker of exquisite instruments was also a maker of peerless tools. We thrill to the playing of the virtuosi of our age. Violinists and their audiences revere the master luthier of Cremona, the Amati, the Guarneri, and Stradivari, who centuries ago invented the modern instrument and built the most magnificent examples. We wonder which tools those great craftsmen might show us with special pride if we could visit them and work. Musicians and composers are just as much intertwined with the artisans and craftsmen who make the instruments as are scientists, both theoretical and experimental, with their tool makers. So from there, from that point of departure, we go on to discuss tools in both theoretical and experimental physics, the people who make them, and how the rest of us benefit from that. One of the most important notions in all of science, and in particular in physics, is the notion of symmetry. The idea that something is before and after, is the same before and after you do something to it. So a simple example from almost everyday life. Think of a droplet of water. Ignore gravity or go to a place where there is no gravity. It will be perfectly spherical, and you can turn it this way and that way in any direction by any amount, and it will still be the same form. So it turns out, and this is a lesson of a century ago, not fully appreciated for a long time, that the idea of symmetries of the laws of nature, so mathematical operations that we can make on the laws of nature as we construct them, lead directly to the famous conservation laws, the law of conservation of energy or conservation of momentum. And so these laws, which once upon a time were empirical regularities that people struggled to define, what's the right thing that you measure that you can say is the same before and after a collision or something like that, they actually come from there, and they are related to the fact that the laws of nature don't depend on time or place. And there are a whole series of these things. And even better, as I'll describe on Thursday for those of you who want to come to a public lecture, it turns out that in a special version of this application of symmetry to the laws of nature, we can actually derive from the symmetries we witness by doing experiments the fundamental interactions. So gravitation, the strong interaction among quarks, the weak interaction that changes radioactive decay, and so on. An amazing breakthrough, led in 1918 by a German mathematician named Emeritus. As I say, on Thursday I'll give a sort of historical talk about Emeritus and a little bit about her work, which was peripheral to her main career as the inventor of whole fields of mathematics, modern algebra among them. But we want to introduce this idea and do it even less technically than I've just done for you by making an analogy to architecture and to slogans in architecture and architectural design principles. So it goes like this. In an 1896 essay, The Tall Office Building Artistically Considered, the American modernist architect Louis Sullivan argued that a structure should not merely recapitulate classical forms, but should express the building's intended uses. All things in nature have a shape, that is to say, a form, an outward semblance that tells us what they are, that distinguishes them from ourselves and from each other. Whether it be the sweeping eagle in his flight, or the open apple blossom, the toiling workhorse, the blithe swan, the branching oak, the winding stream at its base, the drifting clouds, over all the coursing sun, form ever follows function, and this is the law. The law that Louis Sullivan espoused, usually expressed in the alliterative design principle, form follows function, seems self-evidently apt in the context of a Greek temple, a Roman bath, an office tower, or for that matter, a citrus reamer or a graphical user interface. But is it the only productive way to think? Over the past century, physicists and mathematicians investigating the fundamental forces of nature have come to understand the value of inverting Sullivan's modernist motto. We have learned that certain symmetries of nature's laws dictate interactions, which is to say that function follows form. This principle underlies our understanding of the strong-weak and electromagnetic interactions and the gravitational interaction prescribed by Einstein's general theory of relativity. It is truly the key that unlocks our understanding of these fundamental forces. So what we invite the reader to do, and I invoked conversation at the beginning of my presentation, we think of our book as an element of a conversation. So we would like the reader, in his or her mind at least, to be talking back to us. You will bring to the book your own prior experience, your own prior thoughts. Maybe they'll be changed by what we have to say. Maybe you think we didn't get it right, so you can shout back at us or write to us or something like that. But we want it to be a conversation. We want to engage people in thinking about what we write and not taking what we say as the final word, but as an entree to the subject for you to think about. Okay, so this leads us to an introduction, to a discussion of the laws of nature as we understand them today. And what's very exciting for us of a certain age is that over the last few decades, we have actually arrived at two new laws of nature, which we call the electroweak theory and the theory of the strong interactions, quantum chromodynamics. So this is big stuff. It doesn't happen every other week to come up with a new law of nature. And these have been the result of applying ideas developed over the previous century, of meticulous observations done in experiments that give us clues of how to put the ideas together, and of quite brilliant theoretical insights that have led people to speculate about the way things might turn out. One of the things that is wonderful to us, and came through more in writing this book, we've all had experiences in which we have an idea, or someone tells us an idea, we think it's not a bad idea, and then we find that nature takes the idea much more seriously than we do. This will come as a shock to some because it's reputed that physicists and scientists are self-confident, arrogant even, but in fact we're a bundle of contradictions. And the most wonderful thing I know, and I've experienced this on a minor scale, is to have an idea and then find that nature has actually implemented that idea in a way that goes far beyond your original grasp of it. That's one of the most rewarding things that can happen to us. And to see it happen for our own ideas is wonderful. To see it happen for somebody else's ideas isn't so bad. And this has happened again and again in my short career, to see that ideas that seem like, not bad speculations turn out to be the way nature chose to do things. So that's a great lesson. There is a section of the book that deals with the technologies that we employ in particle physics. So one of the important technologies is superconductivity, the idea that certain substances under weird conditions, usually very low temperatures, can conduct electricity without any electrical resistance, so without any waste, without making heat. And that enables us to make the strong magnets that we need to bend particles around in a circle when we accelerate them to high energy, such as is done with the Large Hadron Collider at CERN. This machine that is 27 kilometers around, and if we had to use ordinary electromagnets to do that, first of all, we couldn't reach the energies that we do. It would be about 3.5 or 4 times smaller. And secondly, we couldn't pay the power bill because you'd just be heating the universe instead of doing something constructive. So that is really a key enabling technology for the way we do particle physics today. But more than that, and this is one of these delicious coincidences or junctures that happens, understanding how the phenomenon of superconductivity comes about is the key for us to complete the theory of the weak and electromagnetic interactions. Because I mentioned the first miracle of superconductivity, which is conducting electricity without resistance. There's a second miracle, and that is in a superconducting substance, magnetic fields cannot enter. They penetrate only a teeny tiny distance. And what that means is that the quantum of electromagnetism, the photon, which we ordinarily think about as a massless particle that can travel forever in the universe without being dissipated, unless it runs into something, actually acquires a mass within the superconductor. And that's the key to understanding how the force carriers of the weak interaction acquire a mass. So a technological discovery, miraculous technological discovery, that itself depended on being able to liquefy helium by cooling it eventually to about 4 degrees above absolute zero. So technology to understanding gives us then a clue for how to build a wonderful theory, which is one of the things that I worked on in great detail. We also talk about the technology of accelerators, the technology of the experimental detectors, and the wizards who make them. And among the tools of both theory and experiment is the idea of doing computer simulations by what's called the Monte Carlo technique of taking random events, making a concatenation of them to build a much more complicated event. Those of you who are of an age to have a pension may meet together with your counselor, financial counselor, who will say, we have run 1,000 examples of what will happen to your wealth over the years, and in 95% of the cases, you will have plenty of money at age 95. You don't have to worry about running out of money. So this is the Monte Carlo method. By making different assumptions, they run different things. And if you plan to live to 95 and you're satisfied that you'll have only a 1 in chance opportunity to end up in the poorhouse, good for you, as long as your financial counselor actually included all the reasonable possibilities. Anyway, this method is central to a lot of things that we do in everyday life. Determining the best route for an airplane to fly is done by this kind of simulations. You try out different paths and so on. So it's really important. And we give not only the canonical history of this method, which involves a very quirky character named Stan Ulam, who was one of the mathematicians at the Los Alamos Laboratory during World War II. But we have, as part of our childhood passion for the sport of baseball, because we were American kids, we have learned that the true inventor of the Monte Carlo method was actually a baseball player and baseball coach who invented a game called All-Star Baseball, in which he implemented the Monte Carlo method before it had been invented by the mathematicians. And so Bob and I knew from the age of 8 what the Monte Carlo method was, even if we didn't know the name of it. Anyway, so we do all these things to try to illustrate the different elements of putting together an experiment, comparing an experiment with theory, and so on, making optimizations. As I mentioned at the very beginning, the union, or at least close affiliation of particle physics and cosmology has been one of the great developments of the last 50 years. Many colleagues are now working in that domain. I have a complicated relationship with cosmology. It's not a love-hate relationship. It's much more subtle than that. And I would like to explain to you how it came to be that I have this weird relationship with cosmology. By cosmology, we mean the history of the universe, how from wherever however far back we can go, it evolved to the state that we see today. Okay. It's only disturbing when my phone goes off, so don't worry. Okay, so the ageless question, how did the universe arise, has stimulated peoples the world over to try to make sense of their origins. David Adams Leaming's Creation Myths of the World describes more than 200 traditional accounts, none quite as snappy as these lines from the poet E.E. Cummings in his poem, 1 times 1 from 1944. When God decided to invent everything, he took one breath bigger than a circus tent and everything began. Science does not yet have an answer. A second cosmological query, how has the universe evolved, has become a fully scientific question, but it was not ever thus. Chris recalls, and in the book there are passages from Bob's experience and from mine. I first noticed cosmology when I was an undergraduate at Yale. Our physics professors had the charming habit of providing unassigned reading lists of some of the classics of 20th century physics, many of which were available in Dover reprint editions that cost a couple of dollars. Those were the days. The price of a pig in a blanket at the Yankee Doodle, the local late-night diner. While preparing a term paper on the classic tests of Albert Einstein's general theory of relativity, I was reading through the popular works of Sir Arthur Stanley Eddington, the most distinguished astrophysicist of his time and the most accomplished expositor of Einstein's theory. General relativity reinterprets gravity as a manifestation of curved space-time and vice versa. As the revered Princeton theorist John Archibald Wheeler put it, space-time tells matter how to move, matter tells space-time how to curve. In most circumstances, general relativity's predictions are indistinguishable to very high precision from those of Newton's well-tested theory of universal gravitation. In some special circumstances in which the two theories differ noticeably in their outcomes, nature favors general relativity. It was Eddington who measured the deflection of starlight by the sun during the 1919 solar eclipse, confirming a key prediction of general relativity and making Einstein a cultural icon. The opening sentence of chapter 11 of Eddington's 1939 Philosophy of Physical Science brought me up short. He wrote, I believe there are 15747-24136-275-002-577-605-653-961, 181-555-468-044-717-914-527-116, 709-366-231-425-076-185-631-031-296, protons in the universe and the same number of electrons. You may not think this is quite as catchy as Call Me Ishmael, but these 80 digits got my attention with just the same intensity. How could he know that? I asked myself. When I discovered that Eddington's number, which equals 136 times 2 to the power 256, issued from his fascination with numerology, and that he had done the arithmetic during an Atlantic crossing, I wondered whether old Sir Arthur had gone round the bend. In this, I joined many of his contemporaries. Thus, I learned from Eddington that cosmology was faintly disreputable, the realm of speculation rather than prediction and verification. Cosmology was in desperate need of data. But I also learned from Eddington that maybe, just maybe, you could know, in a crude sense, about everything in the universe. That was astonishing. Cosmology might be fascinating. And over the 50 years or so, since my undergraduate epiphany, in fact, cosmology has become one of our most data-rich sciences, and we know more and more about the universe today and can go look back and see how the universe was then. And in a different universe, for young people who enter graduate school, you go with some idea of what you're going to do, the subject that is most fascinating to you, but based on what you know at the time. And then you meet different people, and the people who are doing the subject that originally evoked your interest may not be the people you want to spend time with, and other people may capture your imagination and you go off in some different direction. So as it happened, I went to a place where I met wonderful people who were doing particle physics, and it's been a wonderful life for me. If I ended up at another place, I might have met the people who were inventing the science of precision cosmology and gone off in that direction. So one shouldn't be too dogmatic about what we hope to do, and it's worthwhile being nimble and changing even in old age and looking at different topics. The last third of our book, quarter third, is devoted to open questions. So things we find interesting, but for which we don't know the answers, and that we think, either in particle physics or in a allied subject, are setting the agenda for what we'll do and what others will do in the next 10, 20, 30 years. So we describe why they're interesting and all of that. We close with a chapter that's called The Best of All Possible Worlds, ? I'll read you just a little bit about that. Gottfried Wilhelm Leibniz is celebrated as a universal genius of the 17th and 18th centuries for his contributions ranging from history and philosophy to mathematics and the sciences. Physicists know him best as the first to publish the calculus, for which he conceived some of our standard notations, and as combatant late in life in a bitter priority dispute with Isaac Newton. Less familiar to us is Leibniz the Christian apologist, preoccupied with the problem of evil. How can an infinitely wise, benevolent, and infallible deity permit evil to exist in the world? The divine wisdom of Leibniz's theodicy from 1710, like an inconceivably powerful, massively parallel chess-playing supercomputer, quote, weighs all the possibles one against the other to estimate their degrees of perfection or imperfection, the strong and the weak, the good and the evil. It goes even beyond the finite combinations. It makes of them an infinity of infinites, that is to say, an infinity of possible sequences of the universe. The result of all these comparisons and deliberations is the choice of the best from among all these possible systems. This justification earned the delicious lampoonery that Voltaire delivered in his 1759 philosophical tale, Candide, a road novella about the tribulations of a credulous and incurably optimistic youth. According to the great fictional buffoon, Dr. Pangloss, Candide's tutor in matters of metaphysico-theologico-cosmology, ours is incontestably the best of all possible worlds. Neither the Iberian Inquisition nor the Lisbon earthquake of 1755 could shake Pangloss's faith in the perfection of his world, but the good doctor did not have a scientist's respect for doubt and uncertainty. Here is Pangloss's confident chorus in Leonard Bernstein's comic operetta version of Candide. Once one dismisses the rest of all possible worlds, one finds that this is the best of all possible worlds. So it might be a little tautological. Conscious as we moderns are of our world's shortcomings, the best of all possible worlds strikes us as an eccentric and ironical estimate of the human condition. All the same, an important and radical idea lurks in the Panglossian or Leibnizian praise the proposition that other worlds could be possible. Might other worlds be possible? Or do the laws of nature, properly understood, lead ineluctably to the world with the character we know? It is a question that fascinated Albert Einstein, who wondered whether God could have made the world in a different way. That is, whether the necessity of logical simplicity leaves any freedom at all. Arthur Schopenhauer, the philosopher of pessimism, concluded that this is the worst of all possible worlds. No fan of Leibniz, he argued in an 1844 essay on the vanity and suffering of life that a world just a little worse than ours could not maintain itself and is thus impossible. If our world is one among many conceivable possibilities, what selected it as the outcome? Are such questions metaphysical or theological? Might they be scientific questions, even as the mountebank's immodest honorific suggests, cosmological? We don't have all the answers. So this is, in fact, an open question for us. It is, as I mentioned, Einstein thought that maybe the laws of nature were so restrictive that they only had one possible outcome. Many of us, having heard that in childhood, thought that must be the way it is, but it's not necessarily. And in fact, most of what we do is based on making more and more detailed measurements, pursuing more and more examinations of nature under unusual conditions, with the hope that we can more and more explain why the world is the way it is, and we've made enormous progress in that line. But it's not clear that that goes on forever, and there is a line of theoretical physics these days that says we are just one of many possible worlds, a semi-infinite number of possible worlds, and you don't have to find an explanation for why this is the way things are, because stuff happens. And in a world populated by human beings, well, of course it was going to be this way. Now, that is a thought that undermines a lot of tradition, but I don't know a way to prove that it's not a possible answer. So this is one of the things that many physicists are breaking their heads on right now to try to think their way through this. So that's my brief tour of our book. I think I'll finish by telling you about the title. So the title is Grace in All Simplicity, subtitle Beauty, Truth, and Wonders on the Path to the Higgs Boson and New Laws of Nature. The title comes from a line in Shakespeare's poem, The Phoenix and the Turtle. There's a wonderful line for which I like the cadence very much: beauty, truth, and rarity, grace in all simplicity. We believe that our laws of nature as we understand them today are simple to explain and based on a few principles. Maybe we don't know where the principles come from. So they're based on a few principles. They're graceful in the sense that we can make solutions to them and compare with experiment, and you don't have to make apologies or invoke the tooth fairy from time to time to make something comes out. And the first part of that quote from The Phoenix and the Turtle, beauty, truth, and rarity. Well, beauty and truth are things we seek, as in the subtitle. Beauty and truth were once upon a time the names given to the two heaviest quarks that are now called bottom and top, which is maybe more descriptive but not more poetic. And rarity is a characteristic of many of the things our experimental colleagues are looking for and finding. So there are new results this week of something from Atlas and CMS that's, I don't know, it's one event out of 10 to the 15th, million, billionth. So pretty rare. Anyway, that's what appealed to us, and so that's our title. Be happy to have a discussion with you, and I thank you again for coming and participating.